before I start my presentation, I would like to acknowledge my co-authors of this study. These are Luijckx, Eddie Ho, as well as 4 undergraduates from the University of Toronto. Furthermore, I need to acknowledge the help from a lot of undergrad volunteers who in total helped count over 1 million animals. So, sexual reproduction is a widespread phenomenon. It occurs in many different species. And one question we can ask is, why is sexual reproduction so widespread? Because sex may not be the best thing to do. If you produce sexually, you need to produce males. And you can see in this figure, if instead of making males, you would produce females, your population growth would be twice as fast. Now, there's a number of hypotheses which basically can explain why sex could be advantageous, and one of them is Hale-Robertson interference. It basically states that the interplay between drift and selection creates an advantage for sex. Now, as that is slightly vague, I'm going to explain that in the next few slides, but before I do that, I would like to remind you all of the concept of Luijckx disequilibrium. So Luijckx disequilibrium is basically just the associations of alleles between loci. So here we see a single haploid asexual individual, and it has 2 beneficial mutations. So here we have 3 more individuals, and we can see that over these 4 individuals in total, our beneficial mutations are kind of scrambled at random, but basically our associations here are just by chance, which means Luijckx is 0. Now, if beneficial mutations occur more than by chance together, what we have is more extreme fitness combinations, and we have positive linkage disequilibrium. Now, negative linkage disequilibrium occurs basically when we have more populations that have, or more individuals that have intermediate fitness. Now, drift does nothing on average to linkage, but by chance it may generate some positive linkage disequilibrium or some negative linkage disequilibrium. Now, let's first look what selection will do when it generates positive linkage. So selection in this case can be really efficient because it sees these 2 beneficial mutations on the same genetic background. There's a large variance in fitness. So selection will basically fix these 2 beneficial mutations rapidly in the population. As soon as they become fixed, the population has all the same associations, so linkage disequilibrium again returns to 0. Now, in case of negative linkage disequilibrium, selection doesn't really know what to do. It sees 2 beneficial mutations, and both of them want to go to fixation, but actually only one can win. So they're competing to go to fixation, and over time, basically that means that negative linkage disequilibrium basically remains in the population because selection has no clue. So taken together, basically drift and selection generate negative linkage disequilibrium. Now, of course, sex can be advantageous because it can break down negative linkage. So it can basically do recombination, bring both mutations on the same genetic background, making selection again efficient and returning linkage disequilibrium to 0. Now, we just saw a case where we just have 2 loci in the selection, but we can have many, many more segregating mutations in the population. So, with increasing segregating mutations, we also expect higher negative linkage disequilibrium, and therefore we would expect more sex. Another way to look at this is, in the first case, where we only have 2 beneficial mutations, we can just do 1 recombination event to bring them on the same genetic background, while if we have like 5, we need many more recombination events to bring them all together. So this notion that more loci in the selection should result in more sex has been shown in simulation studies by Gilles et al. And we can indeed see here we have the increase in recombination, and here we can see that with more loci, we indeed get more sex. This is of course all well in theory, but we have no empirical evidence that it actually occurs in practice. So the question I want to ask today, if there's more loci in the selection, do we indeed get more sex? So we're going to ask this question to the Rutherford Brachiotus calciflorus. This animal can both produce asexually and sexually. And the cool thing is, they basically induce their sexual cycle themselves. So they make a protein which induces their cycle, and their sensitivity to this protein can evolve. So if a rotifer becomes more sensitive to the protein, they will become more sexual. Now, to manipulate the number of loci in the selection, but we can imagine that these different colored dots here represent advantageous mutations to different environments. So let's pretend they're beneficial for temperature, copper, and salt. So if we combine these different environments together, we should get more loci in the selection. Now, this is assuming that basically making more environments generates more loci, and without doing basically a genotypic study where we link genotype to phenotype, we cannot, of course, be sure that this is the case. But we'll assume for now it is. So our experimental design looks following way. We have a control, and then we have the 3 single stressors of salt, copper, and temperature. Then we have 3 where we combine all stressors in 2 combinations, and we have 1 where we have all 3 stressors together. We'll have 4 replicas for each, and 5,000 animals per population. The first thing I now want to show you is that adaptation really occurred. Like Hill-Robertson is the interplay between drift and selection, so we need to basically demonstrate that selection indeed happens. So what we see here is the control, in white, measured in salt environment, and the evolved salt line measured in salt environment, and we can indeed see we have a strong signal of adaptation. The same is true for all our other environments. In each case, we see signal of adaptation, so selection indeed occurred. We can look at this also over time. Here we have relative density on the axis, and we standardize everything by the control, that's why it's relative density, so the control becomes a straight line. We look at what temperature does. It decreases first because they're stressed, and then they adapt and increase in population size. If you look at the amount of sex they're having, which we measure by what we call the egg ratio, which is basically the fraction of sexual eggs produced, we can see that controls never make any sex. However, the temperature populations did show a slight increase in sexual propensity during the period of adaptation. Now, if we look at the salt populations, we see a very similar pattern. There's first a decrease, and then an increase, and during the increase we see a slight spike in sex. Now, the copper populations, we can see a pattern of adaptation, but it seems they never felt in the mood to have sex at all. Now, we look at their double populations. So we can see that they all have a decrease followed by an increase, so they adapt, and we see slight to moderate increases in sex. Now, if we look at our triple combination, we see again the same pattern, but this time we see very high amounts of sex. Now, as the amount of sex are kind of hard to gauge from all these different plots, what I'm going to do is basically plot the area under the curve of all of these in a separate graph, which we see here, and we can see that indeed the population that was adapting to 3 environments had more sex than the 1 to 2, and there's the other 2, and then finally there's 1 which has just 1 environment. There's one problem with this data, and that is that we measured sex in the same environment. So let's imagine a rotifer just sees salt, and it thinks, I'm just going to plastically respond to the salt and have more sex. So it might not be a genetic change. To prove that these changes are genetic, we therefore have to do a common garden experiment where we put them all in the same environment and see if the effects still persist. So that's what we did for multiple time points. Before I show you that data, I'm going to slightly alter this graph to make it more comparable. So this is basically the same data, but just cut off a little. And here we have the data from our common garden experiment. We standardize it again by the control. That's why it becomes a straight line at 0. And we can see that our triple population did increase in sexual propensity over the same time scale, so that looks like a genetic change. We have our double, our other double, and our single population. So we can see the order is the same as in our in situ measures, which basically gives us a good indication that these changes were indeed heritable. Now, we did have some populations that had very low amount of sex before in this graph, so I want to show you the data in a slightly different way, which is basically the total amount of sex, or the average amount of sex they had over the experiment. And you can see, although the temperature copper populations had very low amount of sex, they still had more sex than the two underlying single populations. The same was true for the salt copper populations. They still had more sex than the underlyings. And again, the same pattern for the salt and temperature. And also the triple populations had always more sex than the underlying double population. Now, these were all data from what we call experiment 2, which of course implies we did an experiment 1. And experiment 1 we only did with 2 stressors. And you can see that the data are surprisingly similar. Again, the more complex environment has more sex. So we have 2 independently replicated evolution experiments that basically give the same result. So we started this presentation by asking the question, why is sexual reproduction so widespread? Because sex is not the best thing to do because it has these large costs associated with it. Now, we were thinking that maybe Hill-Robertson interference can explain the evolution of sex, and this theory predicts that with more loci in the selection, higher rates of sex evolve. Now, I kind of cheated here because these are actually our data. We can indeed see that in more complex environments, sex is more prevalent. So I think these results can be important because nature is inherently complex with multiple selective forces acting on populations at the same time. So maybe this will explain why sex is so prevalent in nature. Thank you. I'll take some questions. Yes?
So in order for sex to evolve the way it did, the sexually produced eggs in the experiment have to hatch
Yes?
pretty soon, like
yes.
the time scale of your experiment. But in rotifers, sometimes those sexually produced eggs are, wait on a period of time.
So that's a very good point. We did extra experiments to basically show that 1, the hatching rate is equal in all the treatments, and 2, basically there's a 75% hatching rate within about 5 days of the experiment. So we actually have a very special case of a rotifer population.
Yeah.
They don't do what normal rotifer populations do. They immediately hatch.
Cool. Well, yeah, that's great. Otherwise, it wouldn't work.
Perfect.
You get more sex with more complicated treatments, but in all the treatments, it goes away by the end of the experiment, right?
Exactly, yes. So that's actually what we of course expect according to theory. So this may not explain why sex is so advantageous in nature, unless nature basically selective optima are continuously shifting. Yes?
Maybe you were to, or I'm sure you did. What was the starting stock of the evolution that, was that some diverse?
Yes, so we started with a very diverse line of rotifers. They were made up out of about 200 different genotypes. And like previous experiment, I can talk with you later, time for our next speaker.